Hey everyone, welcome to Insights by Rish. Today we are going to perform image classification using convolutional neural network. In this module, first we will start with artificial neural network. We will see how we can implement the image classification using the ANN, but we'll also understand how the ANN affects the accuracy of image classification, and then we will move towards the convolutional neural network. The dataset that we are going to use in this particular model is the inbuilt dataset from Keras, which is CIFAR10. Let me show you that. So this is the dataset that we are going to use. It consists of 60,000 images, each of 32 by 32 grid, and it consists of color images, which means the channel dimension will be 3, red, green and blue. Here we have 10 individual categories, as you can see, starting from 0 to 9, and this particular dataset we are going to implement, where we will classify the images belongs to which particular category. So let's start coding. First we will import all the necessary libraries that we require. So the very first library that we require is TensorFlow, and we will give an alias TF. Then we also require Keras, which is present in the TensorFlow itself. So from TensorFlow we will import the Keras library as well. Next we will also require the matplotlib library to plot the images. So we will also include that as PLT, and we will also require the NumPy library in the later stages when we are doing some predictions, and also need C1 as well. Now I want to set the size of the image that I will plot. So to do that I will use rcparams function. Actually plt.rcparams. Here I will give a figure.figsize, and I will set it to 15,2. 15 on x-axis and 2 on y-axis. Let's run this. So now we have imported all our necessary libraries. Next thing that we want to do, we want to load the dataset from Keras, and we'll directly load it in a train test split format. So to do so, we'll write xtrain, ytrain, and then xtest, ytest. Here we will load the dataset from Keras. So this is the dataset that we are going to implement, CIFAR10, and .load data. So now that we have loaded the data, it will download it from this particular path. And the next thing that we want to do, we will check the size. xtrain.shape, and we will also check the size of test dataset. And now you can see, out of 60,000 images, 50,000 images are present in the training set, while 10,000 images are present in the testing set. Each image is of size 32 by 32, and every image is a color, hence it have 3 channel dimension, red, green and blue. Now that we have loaded the dataset, we want to plot some images. We want to see that images. So to do so, let us see if we want to check the image at location 1000 from the training set. Let's do this. This is the image, and currently it will show you something in the kind of array format. To plot the image in actual format, you need to use the matplotlib function, and from that you will use this particular function as plt.imshow method, and here you will pass the xtrain at location 1000 as an argument. So let's run this. And this is what you get. This is the image that you get. Now let us check what this image is. From the first view you can say this is kind of truck, but let us confirm it. So we will also print the value from ytrain at location 1000. Ytrain stores the labels for the training set. Now you can see something different here. It gives you the value. It gives you the answer in the form of values. Like if it is 9, then you need to visit the dataset, and you can see at the 9th location, starting from 0, at the 9th location you have truck category, which means the image is classified as truck. But you don't want it in this particular format. You want the name to be displayed, and to do so we will create a list of these categories. We will create the list of these particular categories. Explicitly we are doing so. So this is the list I have created. Starting from 0 to 9 of airplane, automobile in this particular sequence of the dataset. And now we will do something like this. So we'll say classes at location ytrain 1000. Now you will get an error here, and I will let you know. So the error that you are encountering here is only integer scalar arrays can be converted to a scalar index. And let me explain this error to you. When you try to display some values from the training set of the white train, of course, there are some label values. Let's say first 5 label values. You can see that the values are displayed in a two-dimensional format and not in a one-dimensional format, and that's the reason you are encountering this error. To handle this, you need to convert it, you need to flatten this array into a one-dimensional one, and to do so you will use the reshape method. So you will use something like this, ytrain dot reshape, and you will provide the attribute -1 here. So it will convert your two-dimensional array into the one-dimensional one. Let's run this. And now if you try to display the first 5 true labels, let's say first 5 true labels from ytrain, you can see you are getting the answers in a one-dimensional format. Now you won't get this particular error here. Let's try to run this again. Now you can see it's showing the answer truck. So you need to explicitly create the list of categories here, and you need to pass your training label dataset with its index into this particular list to get the answer in the categorical format. Now as we are doing so, why to do this particular thing again and again? What if we try to create a function here? So we'll just call it again and again, and we don't need to write the whole code. Also, what I need to do, I want the label truck along with this image. I don't want to print the true label explicitly and individually. I want the true label along with the image, and to do so I will create a function here. So let us write the function plot image, and here I will pass an index. After passing the index, next thing I will do is I will say plt.imshow method xtrain at location index. So whatever index I will pass, it will be fitted here, and it will show you the training image at this particular index. Next, I also want its true label to be displayed as a title. So to do so, what I will do here is I will say plt.title, and I will say I want the title as ytrain of that particular index. This is what I want. Let's try running this. So now we'll make a function call. Let's say we are calling this function plot image, and we'll pass the index 6000. So we want to display the image at location 6000, and here you can see the image is displayed, but again you can see we have a title here which is the form of a value. So one thing we need to do here, we need to update this function, and we need to say classes. So now it will show you the true label as a title. See, now you are getting your image along with its true label as a title. This is what I wanted, but again I don't want this x-axis and y-axis. I don't want this scale here. So to remove the scale and to only display the image along with its title, we need to do something like this. We will store this whole plt.imshow function into some variable. Let's say we'll store it in figure variable fig, and here we'll say inside the function only that fig.axis dot get x-axis, and we'll say set visible false, and we'll do the same thing. Yes, it should be inside the parenthesis. So we will do the same thing for y-axis as well, because we don't want scale on any of the axis. So to do so, one thing I need to manipulate here is I will say y-axis. Let's rerun this code, and we'll again try to display the image at location 6000. Now you can see we don't have scale on any of the either axis, and we just have the image along with its title as a true label. So now we are done with this. If you want, you can plot some more images. Let us plot one more image here. So let's say we want to check the image at location 450. So you can see the images of dog. So now that you are done with this all things, next thing you want to do is you want to do the data normalization. If you try to check the values, let's say X train at 6000, and just a minute, let me show you the data, because it stores the image in the form of array. So you can see this is the data, and the data is between 0 to 255 range. So in order to increase the accuracy of your model, you need to scale this data, and the maximum limit, or you can say the last limit of this data, is 255. Hence we will divide the data by 255 to scale it. Like in machine learning, we perform various min-max scaler and various scaling options for data normalization. Here we'll simply divide it by 255. So we'll store it in a new variable xtrain scaled, and we'll say xtrain. We won't modify our original variables, we will keep them, we'll preserve them, and we'll just manipulate their values and store them into a new variable. So xtrain divided by 255, and we'll repeat the same thing for xtest as well. So let's say xtest scale is equal to xtest divided by 255. This is what we want to do. We'll rerun this particular code, and let me again try to display the xtrain scale for you at location 6000. So now you can see the values are scaled between the range 0 to 1, and this is what we wanted. So now we are done with this. The next thing that we want to do, we'll start building the model. We are already done with train test split, because we initially loaded our model into the train test split only. So we just want to build our model right now. Now, as I said initially in this video, we'll start by building the artificial neural network model, and then we'll check the accuracy. Then we will conclude some things from that particular model, and then we will move towards the convolutional neural network model. So beginning with, I will write the title here, which is in model, and we'll start building the model. So let us name this as model is equal to, now keras.sequential. So first thing that we'll do, we will add some dense layers here. Now dense layers basically means that every neuron is connected to every other neuron from different layers. Like if you are having just a single layer perceptron model, in that case every neuron from your input layer will be connected to every other neuron from your output layer. So let's say keras.layers.dense, and here we will provide how many neurons we want into our hidden layer. One thing we can also do, we can initially include the flattening layer. So we will say keras.layers.flatten, and here we will say the input shape. Now as I said previously, the input shape is 32 by 32. We also need to provide the channel dimension here. If you are having the color images, then the channel dimension is 3, and if you are having the grayscale images, then the channel dimension is 1. So here the images are colored, hence we will provide the channel dimension as 3. And next, the activation function as ReLU. Now the next thing that we will do, and I don't think we have activation function in the flattening layer. Let's remove this, just keep it as it is, or just with the input shape. And next thing that we want to do here, we will say that, let us say that I want 500 neurons in my first hidden layer, and the activation function I would use is ReLU, because in both, in the binary classification as well as in multivariate classification, you use ReLU as your activation function for hidden layers. Now I don't require to pass any input shape in this particular layer, because I've already passed that in the flattening layer. So this was my first hidden layer. Let's say I want 2 more hidden layers, another with 300 neurons and another with 100 neurons. So these are the 3 hidden layers that I have included, and the last layer would be the output layer. So in the output layer, as we have 10 categories, if you check this data set, you have 10 categories, and hence our output neurons would be 10 in number. So because your prediction will belong to either of these 10 categories, so you have 10 neurons in your output layer, and the activation function here you will use is softmax, because you prefer softmax activation function over sigmoid when you are doing multivariate classification. If you are going for binary classification, like predicting the insurance or loan, then in that case you can have sigmoid activation function in your output layer. So we are done with this. Next thing that we want to do, let's try to run this. I'm not sure whether we have activation function flattening layer or not. Okay, so we don't have, because we haven't encountered any error here. So next thing that we'll do here, perform that in the same cell. So model.compile, we'll compile it, and we will use the optimizer as Adam. Now Adam is currently the most popular optimizer in the neural network domain. If you want, you can go for any other optimizer as well, like stochastic gradient descent, mini batch gradient descent, adaptive delta, RMS prop, anything. But Adam is most preferred over all this. Is the reason is Adam gives you both advantages. It actually smoothens your path to reach the global minima, as well as it gives you the priority of, or you can say the advantage of, adaptive learning rate, and hence you prefer Adam optimizer over all others. Next is we'll specify the loss function that we want. Now we will specify the sparse categorical entropy, and I will also tell you why we prefer this loss function in this particular model. Cross entropy. This is the loss function that we are going to prefer. Now this is because whenever you are performing multivariate classification basically means when you have more than 2 categories in your target feature, like here we have 10 categories. In that case, you prefer categorical cross entropy loss function. But there is a difference, there is a thin difference between the sparse categorical cross entropy and just simply the categorical cross entropy. And the difference is, when you have your target features in a form of one hot encoding, then in that case you prefer simply the categorical cross entropy. Like, let us consider, whenever you check the true labels for this particular data set, you get your answers in the values like 1, 2, 3, 4. So they aren't in the form of one hot encoded, like in the form of zeros and ones. For example, let's say your image, that image belongs to the category frog. So in that case, you will just have the value of frog as 1 and all others as 0. So in that case, your target feature is one hot encoded, that is in the form of zeros and ones. In that case, you use categorical cross entropy. But whenever you are having the original values and you don't have any one hot encoded in your target feature, then you prefer sparse categorical cross entropy. And last, we'll prefer on what basis we want to evaluate our model. So we want to evaluate our model on the basis of accuracy. So let's prefer that. Now we are done with compilation. The last thing that we want to do here, we will train the model. So model.fit, we will pass the scale data. So x train scaled here and y train. We will specify the number of epochs that we want. So in this case, I want 10 epochs. Initially, you always start with less number of epochs, and depending upon the accuracy and overfitting and underfitting of your model, you increase the number of epochs purely based on trial and error. Now I will also specify the batch size here. So I want 100 as a batch size, that is in every batch 100 instances would be passed. So let's run this. It will take some time. So till the time epochs are running, we will try to print the loss and accuracy here. We'll just write the syntax for the same. So loss comma accuracy, it stores both the values here. We'll say model.evaluate x-test. We'll evaluate our model on x-test and y-test. Actually, the x-test scaled here. And we'll print the accuracy. We won't print the loss here because we just want to look at accuracy. And we'll multiply it by 100 because we want our accuracy to be in the format of percentage. While the epochs are running, the accuracy that you are seeing here, this is the accuracy on your training set, as we have just divided our data set into the training model and the testing set. So in this case, we don't have validation set here. So this accuracy is on our training set, and we are going to evaluate our model on the testing set. So I think we are close to, we are done with 10th epoch. We are done with 10th epoch, and you can say at the end of 10th epoch, the accuracy on the training set is 52%, which is kind of very low. Let us evaluate our model on testing set as well. So you can see the accuracy is just 49% on the testing set, and this is because we are using artificial neural network for this purpose. So though you can perform your image classification using artificial neural network, but in that case you need to compromise your accuracy. because whenever you are preferring artificial neural network over the convolutional neural network for image classification purpose, in that case the accuracy is kind of very low, because actually your artificial neural network cannot handle such complex data sets like of images. It can go with any numerical data sets that you have in machine learning. So now you can see the accuracy is very low when you are preferring the ANN model. So next thing that we will do, we will perform the same thing using the convolutional neural network model. So let me copy this particular code and I will paste it here. So I will label it as the convolutional neural network model, CNN. So this is here we'll build our CNN model with the name CNN underscore model. So let me modify the name on every instance. Now this particular layers that you are seeing are the dense layers that are the part of artificial neural network. Though we are going to incorporate these layers into our convolutional neural network as well, but before that we need to have some convolutional layers, some pooling layers as well. So let us say that this was the dense layers, and now we need to add here the convolutional layers. So to add the convolutional layers, it depends upon you how many layers you want to add. I am going to add 2 convolutional layers here. So the first thing I am going to do here is start with adding the filters. So keras.layers.conv 2D, and here I will pass the filters. So the number of filters that I want, it completely depends upon you how many filters you want. I want 100 filters in my first layer. And the kernel size. The kernel size is basically the size of grid of your filter. Like if your filter is a 4x4, 2x2, 3x3. So I want my filter to be of size 3x3. And next you will include this input shape, which is currently present in the flattening layer. So you won't require any input shape in this particular flattening layer. You will just specify your input shape in the first convolutional layer itself, and then the activation function. So here as well you will prefer the ReLU activation function. Now this is the first convolutional layer. After this we need to add a pooling layer, because we want to do either the max pooling or the average pooling. So we will do the most popular pooling, that is the max pooling. So keras.layers.max pooling 2D. And here you will just specify the size of the max pool you want. So I want it to be 2, 2x2. So this was my first convolutional layer. In the similar pattern, I am going to add one more convolutional layer along with the pooling here. Let me copy paste the code. So this particular layer, and in this layer I want 50 filters. I have reduced the size to half of the first layer, and the kernel size and everything else remains same. You don't require the input shape in the second layer. You just need to specify it in the first layer only. So now you're done with that, and everything else remains same. So now this is a convolutional neural network that you are building. So yeah, let's try running this. Okay, so it started building now. It will basically consume a lot of time. So now that it's trained, we will try to predict its accuracy. So I'll copy this code from here and let me paste it here. This model is named as CNN model. So let us name it as CNN model, and we'll evaluate it on the scale data. So let's try and run this. So here you can see one thing is when you used ANN model, in that case the accuracy on your training data was 52% and on your testing data was 49%. In CNN model, when you use a convolutional neural network model for image classifying, then in that case your accuracy on the training set increased drastically. Like now it is 92%. It grew up from 52% up to 92%, I think, which is an increase of around 40%. But and also the accuracy on your testing set has increased up to 70%. Initially it was 49% and now it's 70%. But still you can see that the difference between the accuracy on the training set and on a testing set is quite large. The difference is around 22%, which means your model is doing great on the training set, but it's working poorly on the testing set, and this is a kind of overfitting condition. So in order to handle this overfitting condition, though your accuracy, both the accuracy on the training set as well as on the testing set improved as compared to the artificial neural network model, but still there is a problem here that the model is overfitting because it is giving you good accuracy of 92% on your training data, but when you are testing it, you are evaluating it on your test data, then it's working poorly as compared to the training set. So in order to handle this, you can add a dropout layer, which is a kind of regularization in the deep learning. Like in machine learning, you have lasso regression and ridge regression as your regularization techniques. Here you have dropout layer. So let's say keras dot layers dot dropout. And the good practice is to add the dropout layer after every hidden layer. So here I will specify the dropout rate as 0.2, which means randomly 20% neurons will be deactivated in each layer. So I will specify this particular dropout layer after every hidden layer. And so we have 3 hidden layers, and hence I have specified 3 dropout layers as well. And then we will retrain the model. We'll again check the accuracy. So the training accuracy is 85%, which got reduced to 5% initially. Before adding the dropout layers, it was around 92%. So there's a drop of 7% there, but that's not a matter here. Just we want to reduce the difference between the accuracy on the training set and testing set, so that we can say that our model is performing well on both the sets. So here you can see the accuracy is 72%. Now the fact that it is 72%, it just got increased by 2%. Initially it was 70% before adding the dropout layers, and now it is 72%. So but the thing is that when before adding the dropout layers, the difference between the accuracy of the training set and testing set was about 22%, but now it is around 13%, which is good, I feel. So if you want, you can if you want to reduce this difference more, and if you want to reduce more overfitting, and if you want to gain more accuracy in the testing set as well, one thing you can do here, you can increase the dropout rate here. I only deactivated 20% neurons in each hidden layer, and though we have a lot of hidden neurons here, in every layer we have hundreds of hidden neurons, so in that case the 20% deactivation of neurons is quite low. So what you can do, you can increase this dropout rate in order to increase the accuracy on the training set as well. But I think this is good. So now that we are done with everything, we'll try to evaluate our model. So to evaluate our model, so first we'll make some predictions here. To make the predictions, what we'll do, we will first modify the code that we wrote initially, and the code was somewhere here. Yeah. So here we are explicitly taking x train and y train. Instead of that, we will specify x and y values, and here we will take for x, and here we will take for y. Now the x can be your either x train or x test, and y can be your either y train or y test. So I think that's it. Let us run the code again, and here the thing that we will do here, we will say plot image. So now let me check the code once again. Yeah, so in this code, yeah, so on the place of x we will have x test, and on the place of y we will have y test. We want to check the actual image and the true label, which is stored in y test, and then we will pass the location. So I want to check the test data at location 250. Let's consider this, and we'll plot the image. So there is again we are getting this error because we again need to reshape the test labels. So y test is equal to y test dot reshape, and we'll flatten it, we'll make it one dimensional. We'll again run this. So now we won't encounter that particular error. So at the location 250 of the testing set, we have the true label as dog. So now we will check what our model is predicting, though the model won't give us 100% accurate predictions because the accuracy is quite low here, as we had a very low dropout rate here, and also the less number of epochs. If you increase the number of epochs from 10 to 100, and you also increase the dropout rate to around 0.4 or 0.5, in that case you would get the good accuracy on the testing set as well. Now let us say what let us check what our model has predicted. So when you actually do the predictions, let us store that in pred variable. So this is, I think, CNN model dot predict for X test field, and let's run this. Now when we check our values at location 250, we want to actually want to know what our model is predicting for the image at the location 250 of the testing set. So for that, when we say pred of 250, in that case we will get an array, because you are using softmax activation function in your output layer, which will give you the probability of every category here. So you want to identify the maximum value of the category using the numpy library that we imported in the initial stage of the video. So I think we will use np.argmax, and in that we'll pass this spread variable. So we will get the location at which we are having the maximum value. So at the fifth location we are having the maximum value, and we want to check what is at the fifth location. So we'll pass it to the list of classes that we created. So the list of classes that we had, or we can say the list of categories that we had. So we'll pass this to that list, and we'll say that our model is correctly predicting it to be dog. So the true label is dog, and our model is also predicting it to be dog. Let us do some more predictions. So let me copy this particular code, and I want to check what is at my location. I'm giving some random values here like 899. Again the dog. Okay, let me check change the value here, 199. So it's a ship. So at the location 199 of the test set, it's a ship. Let us check what our model has to say. So let me just copy this syntax from here, and at the location 199. Okay, so model is again doing correct classifications. We are fortunate enough that here in this case, both the times when we tried to make some predictions, our model predicted correctly, but as the accuracy is 72%, it won't happen for every prediction. There would be some predictions where you will get some misclassifications as well. Let me do one more prediction here. I will try to change the value from 199 to 799. So at 799 we have a bird, and let's say what our model, and let's see what our model has to say. So at 799. Okay, so it's predicting bird. So as I said previously, we are fortunate enough that every time our in this particular model, our model has done correct predictions. But when I was trying this particular previously, 3 out of 2 were correct, and 1 was a misclassification, of course, as the accuracy is 72%. So okay, the model is kind of good here. But if you want to increase the accuracy of the testing set, you can change the dropout rate, you can increase the number of epochs, you can reduce the batch size as well, and you can try to add more convolutional layers, some more dense layers, depending upon your trial and error basis. You can also increase the number of hidden neurons here. Now but the optimizer and the loss function, everything in the compiled syntax would remain constant. Now that we are done with predictions, we'll try to evaluate our model, and to evaluate our model we will use two most important metrics, confusion matrix and the classification report. So from sklearn.metrics we will import the confusion matrix, and we'll also import the classification report. Now we want to print the classification report first. And to print the classification report, we'll pass the actual value, which is stored in the true label, which is stored in whitetest. And here we simply can't pass the pred variable. If you have watched the machine learning tutorials, in that case we pass the true labels, that is whitetest, and the predicted labels, pred. But here we are having continuous values in pred. So if you try to pass the pred variable here, you will encounter an error. So you can see the name classification is not defined. Just a minute. So this is a classification report. Let's run this, and you will of course encounter an error here, because in your pred variable you are having continuous values and not just a single value. So as I said, we are getting this error like classification matrix can't handle a mix of multi-class values, because the pred variable is consisting of continuous values. As we saw previously, it consists of probability values for every category, and from that the index at which we are having maximum value is the true label. So one thing we can do here, instead of just passing the pred variable, we'll pass np.argmax. That is, it will extract the maximum value from this particular probabilities. We'll pass something like this. And now let us try to run this. Error that we are encountering here is because it is just considering a single value, like if you are having 10,000 instances here, it is considering the argmax value just of the first instance. So what we need to do here, before this particular, we need to make a new variable. Let me paste this code here. And here what we are doing, we are extracting the index of maximum value from every pred variable in a pred value. So let me run this, and then instead of passing this, we will pass pred value here. Now let's try to run this. Now we are getting our classification report. So in this case, you can see this is the F1 score, the accuracy is around 59%, the precision, and this is our classification report basically. And you can see the highest precision is for the class 4th, and I think the class 4th is of deer. So the highest precision is for this particular class of deer, and the lowest precision is for the class, I think it's for the class 3. So let us check. The class 3 belongs to cat. So the lowest precision is for the class cat, and the highest is for the deer one. Now that we have printed our classification report, next thing that we will do, we will print the confusion matrix. And to print the confusion matrix, we will say CF, into which we will store our confusion matrix. So confusion matrix, and we will say that we are passing here the true labels which are stored in y-test and the predicted ones which are stored in pred value, and we'll say normalize is equal to true because we want our value to be normalized in a decimal format and not in some exponential one. We'll say true, and then we'll plot the heat map using the cbun library that we have imported, and then we'll use the cbun heat map function to plot the heat map. So here we'll pass the confusion CF confusion matrix variable, and we'll say the C map is equal to blues, which means we want the theme of our heat map to be blue, and we'll say anot is equal to 2 so that the values will be shown on the grid. If you don't want your values to be shown on the grid, you can just say false, anot is equal to false, and let me run this. So this is the heat map that you are getting. In a diagonal, you can see in a diagonal way, the grids are dark, which means the classifications, the correct classifications are higher compared to misclassifications, because in a diagonal pattern you are having the values for all correct classifications. Like consider the first column, on the y-axis you are having the value 0, and the x-axis also you are having the value 0, which means for the dark column the actual value, the actual image belongs to the class 0, which means the class airplane, and 74% time it's happening that your model is also predicting it to be the airplane category. So this is how basically this particular heat map gives us an insight of our model. So this was evaluation of the model, and from all this we came to a conclusion that though we can perform image classification using artificial neural network, but in that case we need to compromise with our accuracy, because while you're performing image classification using ANN model, you won't get high accuracy, because using ANN is not a good choice for any image classification projects. So the convolutional neural network is best choice for either the object detection projects or for the image classification projects, and you need to increase your dropout rate, and you need to introduce some dropout layers in order to handle the overfitting of your model. So this was the image classification model using the convolutional neural network. That's it for the video. Thanks for watching.